Ok, estamos ao vivo. Bem-vindos a mais um seminário organizado pelo Departamento de Engenharia Civil e Ambiental da PUC-Rio. Hoje teremos um seminário internacional. O tema será monitoramento em barragens. Sem mais delongas, eu gostaria de passar a palavra ao professor Alberto Saião, que irá fazer a abertura do seminário. Bom seminário a todos.
Boa tarde a todos. Bem-vindos a mais um seminário da PUC-Rio. Obrigado por prestigiarem o nosso seminário. Como disse o professor Alessandro, hoje é um seminário internacional com a presença do Dr. Marr. Quem vai apresentar o Dr. Marr é o professor Pedrito Rocha Filho. Então, eu já passo a palavra para o Pedrito para fazer a introdução. Muito obrigado.
Well, first, I'd like to say thank you to Alan to have a time, or to find a time in his very busy agenda to deliver this very interesting seminar. And with his permission, I have to move now to Portuguese to make the introduction. So it's not because I could not do it in English, but in Portuguese, you'll be more fluent. It's so vast, your experience. And I have to talk about your academic, your professional,
no,
you know.
keep it short.
So I moved to switch to Portuguese now. Boa tarde a todos. Eu já agradeci o Dr. Marr por ter encontrado um tempo nessa agenda dele, que ele é uma pessoa extremamente, como vocês vão ver nessa breve introdução que eu vou fazer sobre ele, e para fazer essa apresentação muito interessante, né? O Dr. Marr se doutorou no MIT, e sob a orientação do também extremamente conhecido, um dos ícones da geotecnia mundial, que é o William Lamb, né? Foi orientador dele, e a tese de doutorado dele foi sobre medidas de tensões totais em barragem. Então, ele já teve uma tese aí de instrumentação. Mas depois ele abriu, depois de se doutorar e passar um tempo no MIT, trabalhando, inclusive, com o professor Lamb, ele, então, fundou e lidera a empresa chamada Geocomp. Essa empresa é uma empresa americana, é uma das principais fornecedoras nos Estados Unidos de monitoramento de desempenho em tempo real, via web, né, de estruturas de engenharia civil, incluindo barragens, diques, escavações profundas, muros e contenções, túneis, edifícios, pontes e serviços públicos, né? O Alan também possui uma vasta experiência em testes de laboratório e de campo para medir as propriedades mecânicas e materiais, né, de solos geotécnicos, etc., projetando estruturas de terra, determinando as causas de baixo desempenho de estruturas geotécnicas, envolvendo medidas corretivas de baixo custo para projetos problemáticos de gerenciamento de risco. É interessante também mencionar que ele liderou essa vasta equipe da Geocomp, no projeto Construção e Monitoramento de Cortinas, né, de contenção em escala real. Isso foi um projeto financiado pelo National Research Council dos Estados Unidos, mais ou menos em torno de $1 milhão, e ele foi o coordenador desse projeto, né, de pesquisa. Ele também projetou e supervisionou o trabalho para instrumentar e monitorar a fundação reforçada geossinteticamente e as contenções dessa nova ponte, que tem o nome do presidente dos Estados Unidos, ex-presidente, do Woodrow Wilson, né? Também liderou um esforço, isso eu tomei conhecimento lá há muito tempo, multimilionário da Geocomp, para atualizar o sistema de monitoramento em tempo real da TVA. A TVA é a Tennessee Valley Authority, e as avaliações de estabilidade de mais de 20 depósitos de resíduos de cinza de carvão, além de ajudar a economizar nesse projeto mais de $100 milhões de custos desnecessários na estabilização dessas obras da Tennessee Valley Authority. Ele também foi o líder e também do sistema de monitoramento por web, que é um sistema muito utilizado, que é o sistema hoje chamado iSite Central. Depois eu vou mencionar rapidamente esse iSite Central, porque nós estamos com um projeto utilizando ele aqui no Brasil. Ele foi um engenheiro geotécnico, um líder em inúmeras investigações de falhas, de roturas de barragens, incluindo a barragem de rejeito de Phelps Dodge, né? O represamento de resíduos de carvão de Buffalo Creek, roturas de barragem de Nova Orleans, principalmente na época do furacão Katrina, e várias outras roturas, né, de barragem de rejeito na Flórida. Uma coisa muito interessante também que o doutor Marr, ele atua muito nas associações técnicas, né? Inclusive, ele é membro da Academia Nacional de Engenharia dos Estados Unidos e, recentemente, atuou como presidente da American Society of Civil Engineers, dos Geoprofessionals, né? Ele é também a Geocomp, ele é fabricante de equipamentos de laboratório e já com muita presença no Brasil. Várias empresas, inclusive, utilizam, universidades, utilizam o equipamento da Geocomp. Tá? E, finalmente, né, além dessa vasta experiência e dessa visão empresarial, essa série de FMGM, Field Measurement in Geomechanics, nós já chegamos, lembro que o 10º foi realizado aqui no Brasil, em 2018, que eu fui o chairman, mas o 7º, que foi realizado em Boston, foi, então, o chairman foi o Dr. Alan Marr. Aqui no Brasil, ele tem já uma presença marcante. Nós já coordenamos um projeto no Banco Mundial, temos agora um projeto que estava em andamento, sofreu uma defasagem muito crítica com essa pandemia, que é o projeto da Light, um projeto de pesquisa e desenvolvimento conjunto com a Light. E nós temos também outros envolvimentos aí em projetos conjuntos. É um grande amigo, uma pessoa que eu respeito muito, uma pessoa que eu tenho uma admiração tremenda pela sua seriedade, pela sua competência, pela sua dedicação. Eu tenho certeza que vocês vão gostar da apresentação do Alan. Então, so Alan, I finished your presentation, a very short presentation. Now, I move to you to make your presentation, okay? Thank you very much again.
Well, thank you very much. I'll just get my share screen going here.
All right.
Okay. Well, thank you. Can you see my screen okay?
I'm seeing it okay. For me, it's okay.
Great. Well, thank you very much for this invitation. I'm very excited to do this. I wish I could be there in person. As Professor Oak will tell you, we've had many good evenings of Brazilian food and wine that I miss, and I can't wait to get back. So hopefully that'll happen soon. I was asked to speak on the use of instrumentation monitoring in dams. And so I thought it'd be best to kind of focus on an overview with where modern technology is, what it can do for us, and particularly with an application to helping us to manage risks. This is very much in the news these days with the number of recent failures around the world and society becoming much more concerned about dam safety. So can we use instrumentation monitoring to help us? We're going to cover these various topics. Why and how do dams fail? Why instrument and monitor? And then what is an effective performance monitoring program? We can't just go out and monitor. It's got to be done in an effective way. I'll review a little bit what can we measure, particularly components of modern measuring systems. I want to talk about the importance of real-time monitoring. Historically, with a lot of water-type dams, we tended to drift into monitoring once a quarter. In my view, in today's world, that's not adequate. And then I'll review some keys for successful performance monitoring based on the experience of myself and my colleagues. I will skip a few slides in here. I know this is going to be shared with some students, so I left a few slides in to elaborate on some topics. So we don't have time to cover all those, so I'll skip a few as we go along. I want to start with a question: are we doing things the right way, considering that dams have failed and continue to fail? Just a few perspective statistics here. A modern water storage dam historically is shown to have an annual failure rate of about 1 in 10,000 over its life, or half of those occur during first filling, so about 0.5 times 10 to the -4 after successful first filling. That comes from my colleague Greg Becker and colleagues. That number has been challenged many times since 1981. It seems to still stand up. And some work I did a couple of years ago also seems to stand up by others, that tailings dams have an average failure rate of about 10 times this value. Now that's a rough number. The key point there is that it is higher, significantly higher than for modern engineered earthen dams for water storage purposes. If you just simply say, what does this mean? Considering that a dam might be expected to last on the average of about 100 years in today's world, then that means the chance of an average modern dam might fail during its lifetime, if it survives first filling, becomes about 0.5%, or 1 in 200 that it might fail sometime during its operational life. Considering that a tailings dam might have an operational life of about 50 years before we go into closure and hopefully into a safer mode, the chance an average tailings dam might fail during its operational life becomes about 5%, or 1 in 20. When you take these probabilities and you combine them with potential consequences of a failure, consequences to people and improvements downstream, then these failure rates can lead to quite high risks to society for certain dams in certain locations. A dam that's out in a remote location with low consequences maybe not as concerning to us as something that's above a city. Just to review a few recent failures to see what we can come out of that, get out of those. There was a major failure a few years ago in Canada, 40 meters high tailings dam built by the centerline method, sudden failure with no warning. There was some instrumentation in this dam, but not very much. Its consequence is that it created one of the largest environmental disasters in modern Canadian history. So while this was a waste dam, might not considered to be very important, it in fact was in its consequence. It cost quite a bit of money to clean it up, and there was a big lawsuit, including engineers being charged for negligence. And it changed Canadian dam safety laws to a whole new set of requirements now for safety of tailings dams in Canada, which is setting the pace for the rest of the world too. There was a that particular one was looked at by some famous engineers, including Dr. Morgenstern, who determined that the cause of failure was a failure through a weak foundation clay that became normally consolidated under the full added height of the tailings. And that brought it to normally consolidated shear strength, and it, as a result, by continuing to add material, experienced an undrained failure. This failure mode was not anticipated because the engineers who designed it never anticipated it becoming normally consolidated material. There was instrumentation. There were piezometers installed, but they were of the type that were unable to measure undrained pore pressures induced by shearing during the last stage of loading. A common problem we see with instrumentation. It's there, but it doesn't detect the warning signs that are really meaningful to us. To look at another one, Oroville Dam, some of you may know, is the tallest dam in the United States, tallest earthfield dam. It was built in late 60s, serviced very well for many, many years. But then in 2017, we had a major failure of the spillway, and you can see the main spillway here is all washed out. This created emergency evacuations downstream of about 200,000 people, so there were very significant consequences here. No one's life was taken, but it cost $1 billion, a little over $1 billion, to repair and rebuild this spillway. There was no active instrumentation in either this spillway or the associated auxiliary spillway, but there were visual indicators of potential distress that were not picked up on. And I'll give you an example here. I don't know if you can tell, but where my cursor is are flows coming out of the underdrain system that are very substantial, and was a visual indicator that this dam was not this spillway was not performing as designed. Now, people claim that this was not a failure, and in fact, it wasn't, in the sense of loss of reservoir contents, but it was loss of a major facility that cost a lot of money to fix. There was another one, Kingston, which is a fly ash storage facility in Tennessee for one of our clients, and this was a sudden failure that was the result of an undrained shear along a previously unknown thin seam of muck. That's this zone down here across the bottom. It was basically a slimy-like material. They were filling and adding to this cell at a fairly rapid rate, and it suddenly generated an undrained failure, which then triggered a flow slide of the sluiced ash, which is a hydraulically placed material at very low density, and therefore prone to or susceptible to static liquefaction. There was instrumentation, actually quite a bit of instrumentation in this facility, but none of it was designed to reveal behavior of this critical zone, since that zone was not known to exist. This could probably have been detected with real-time inclinometers had they been placed in the right place, but that required somebody to anticipate that failure mode, which had not happened. My comments here are not a critique of anyone, it's just a reporting of observations and facts and what can we learn from those. Here in the United States, we had a recent failure. By the way, this is significant in that it greatly changed regulation of these types of waste storage facilities in the United States, causing our Environmental Protection Agency to get much more proactive in designing these. Owners today of these facilities are spending a lot of money to upgrade the safety of these facilities. Recent failure of a water storage dam, only about 32 feet tall. And there was quite a bit of damage downstream, a loss of the structure, which was a part of a hydro scheme. And what's really significant of this is that the latest independent report suggests that this was a static liquefaction failure, which is very rare in an earth-filled dam used for water storage purposes. But there's no known instrumentation in this dam for performance monitoring. Interesting question of should there have been? Switching from these failures to kind of show that failures occur and we many times just don't pick up any information from the instrumentation because it wasn't properly designed or didn't exist in the first place, and many times isn't interpreted properly. Let's look at failures a little bit more. This is a summary of the American State Dam Safety Officials a database of dam failures, which they keep, and they try to keep track of what causes failures. And I think it's very significant to look at this set of data for 20 years to see that by and large, the largest is overtopping failures that lead to a breach. And then others are unknown, can't really be chased down, followed by piping, spillway failures. The thing that we as geotechnical engineers worry about an awful lot, pay a lot of attention to, slope stability and internal erosion fall down quite far on this list. That's not to say they aren't important, but if we're really going to have an impact, we really need to pay a lot more attention to these predominant failure modes, which are somewhat hard to instrument and monitor, but they require our attention. These are dams, just to remind you, these are failures of dams that have an average failure rate of about 1 in 10,000 per year. Looked at from another way, that same database has been put together in a more of a mechanistic or driver of the incident. And I think it's quite interesting to see here that by far the largest cause is hydrologic flooding events, followed by seepage and internal erosion. And then unknown factors and deteriorating conditions. Again, structural stability that we worry a lot about as geotechnical engineers is a fairly low issue here. We need, when we're talking about instrumentation monitoring, we need to really keep these kinds of things in mind. And to me, a big message out of this is that water is really the driver of most dam failures. Now, that may seem like a stupid comment. You know, it's obvious, it's a dam, it holds water. But it means that we really need to understand and control how water gets into the dam and flows through the dam, and how we make it deliver acceptable performance under all imaginable conditions. Looking at a moment at tailings dams, nice paper done kind of summarizing worldwide history on what are the causes of failure. And then we see something different than what we saw in the water retention dams. Here we have a lot more geotechnical type failures, seepage, foundation failure, earthquakes, and then others involved a lot of geotechnical reasons as well. Overtopping is much less of an issue, and those of you who work in tailings dams will understand that. We don't have a big rainfall collection basis feeding water into our reservoir. We just don't have that driver present in most tailings dams. But this means we need to kind of think differently about how we might instrument and monitor tailings dams compared to water retention dams, because the predominant failure mechanisms are different. So looking a bit at why do we instrument and monitor dams, and it really is to help us answer important questions. Some of you may know the famous early instrumentation man named John Dunnicliff, who wrote the only real book on geotechnical instrumentation and monitoring. 1993, John died recently, unfortunately, but I'd like to just acknowledge his great contributions to our field. And he had a statement in which he would say, for instrumentation, you really need to have a question. Instrumentation is to help answer important questions. If you don't have an important question, you don't need to instrument and monitor. Keep that in mind, because many people lose sight of that fundamental purpose. So we have questions like, is the dam performing as expected? Are the current conditions safe ones? Is an emergency condition developing? Is a critical failure mode likely to develop in the near future? These are kind of similar questions in ways, but just asking them in different ways to get people to think outside their normal modes. Will the dam remain safe in the future? And what action should or can we take to preserve or restore the safety of the dam? These are important questions. And if we can use instrumentation to help us get substantive answers to these questions, then it has a real value. I want to talk a moment about failure, because traditionally we as dam engineers have tend to think of failure as loss of containment. So that's really coming out of the water retention world, where once we started to lose containment, the dam was almost assured to completely fail and flood downstream. But in today's world, we really need to broaden that, because dams are of different types, serve different functions, and the demands of society are much more today than just simply avoid failure. So I've added to this, the collapse or loss of containment is kind of a low probability but a high consequence event. But we can add increasingly a concern about resilience. Can the facility remain operational after a major storm brought on by global warming, for example? In this case, it can't be restored to perform its intended function. How can instrumentation help us on a facility that's been damaged to tell us, yes, we can reuse it, or no, we can't? It requires major rework. And then loss of serviceability. Increasingly, it's important that our assets after an event be operational, remain operational. They got to be able to continue to perform their intended function, or maybe they deteriorate over time to the point that they can no longer service that function and we have to take them out of operation. These are higher probability events with lower consequences, but high probability times lower consequence may still be a very significant risk, almost in similar magnitude as the above loss of containment, low probability, high consequences. So we really need to broaden our view when we're talking about monitoring a dam to help preserve safety, to help manage risk, to look at these different measures of failure to perform. I'm going to use failure in the rest of this presentation in this broader context, not only of collapse, but of loss of function. So just a few thoughts about performance monitoring. You know, it's done to indicate unexpected performance before the consequences become large and costly, hopefully so we can intervene and change those consequences or avoid those consequences. In order for it to work, it tells us when we implement a contingency measure to help us reduce those unexpected consequences. And it helps us spot emerging risks early so we can apply risk mitigation measures efficiently. Increasingly, dam owners are making use of risk registers and risk assessment and risk management techniques and technologies. And I think monitoring provides some key data to enter into those risk management strategies. That's an emerging concept I've talked about for 10 years now, and it's being adopted by more and more folks. Managing risk saves money. So this really is telling us that a good instrumentation monitoring program ultimately saves an owner money through managing risk, lowering risk. And so as a result, I conclude that performance monitoring should be integrated with every project's risk management program. I don't see it done that way that often, but it really should go together with risk management. There's all kinds of reasons to monitor performance of civil works. I won't go through all these. I wrote about this. If you can't get this particular publication, feel free to contact me by email. I'll be happy to send you a copy of it. But it describes, these various means and reasons for why, and if we're going to go ask for a budget for instrumentation monitoring, we need to really have a good justification. That's one of the reasons I tried to write on these, to help you formulate reasons, rationale for getting approval of funds to do a good performance monitoring program. These are all various reasons. I won't go through them. But if you think about them, you go back to their root, they really are all aimed at helping us identifying, managing risk in some way. And so risk and risk management is at the heart of dam safety, and it's a key driver for why we should instrument and monitor. This is a busy slide, but I just focus on the key message of this slide. I put together, going back to this number that we had of a dam we had at the beginning of the presentation, a dam that's well engineered in the modern world has a annual probability of failure of about 0.5 times 10 to the minus 4. But how might monitoring help us lower that? Suppose we have a huge population downstream or a nuclear power plant downstream. This might be too high of a probability. And so I worked out what's called an event tree to trace out how things might develop and how interventions might change probabilities. And I won't go into these details, but the point is, if I instrument and it's successful in detecting poor performance and I implement my corrective actions properly, then I can lower, in this example, I can lower my probability of failure by roughly 10-fold. And depending on how you work with these probabilities, you can prove that a good monitoring program can reduce risk by 10 to 100 times. And that can be very, very cost effective. I urge some of you who are challenged by how to justify spending money on instrumentation and monitoring, think of it in kind of the context of this event tree and put the numbers together to help show management that there is a good basis, good money basis, financial basis for doing good performance. Now, I keep talking about good performance monitoring or effective performance monitoring. What do I mean by that? I mean that we've got to collect and use observations and measurements to quantify how a structure is performing its intended geostructural function. It's not just taking data and making a nice plot and a pretty color chart report. It's doing something to help understand how that structure is performing, to help answer questions like, is it meeting its design requirements? Will it continue to function? Will there be a time when it won't function? And what can be done to improve performance? Many times you'll know we'll go and say, well, this dam looks like it's not working right, so let's spend $10 million doing this. It's kind of like a Band-Aid thing. Well, with instruments, we can get a much better idea of why is it not performing right, so we can target that remediation work to the real root cause of the problem. And effective, what does effective mean? It's producing a desired outcome or end result. And so effective performance monitoring is really obtaining and using data and observations to help ensure the facility will perform its intended function, that other facilities are not damaged, and that impacts to the neighborhood are minimized. You know, I urge us to really all think more broadly about the role of performance monitoring in helping not only save the facility, but preserve our people and the environment. So there's some challenges that come about trying to do effective performance monitoring, and I just raised some questions here. I'm sure many of you who work in this world have faced these questions, you know, where, how often to read, how to get the data into a meaningful way to decision makers so that they can believe it and act on it, how to sort out what are warning signals and what actions to take. You know, you get a new high reading. Is it a warning indicator or is it an outlier? These are all very challenging questions, but if you've got a good team together, and they can address or develop strategies to address these questions usually. Just to pick on a couple of these in a little bit more detail, the question of what and where to monitor, I would urge us to start thinking a little differently than when you have in the past, where we had a tendency to take a cross section and start putting a bunch of the symbols on the page. You know, I think we need to back up and think more about what are the potential failure modes. Those of you involved in dam safety assessments these days know that we have moved towards potential failure modes assessments. That's a good starting point for you to then say, okay, for this potential failure mode, what instrument can I put where to tell me that this potential failure mode is developing and evolving? It really helps you focus your efforts and point things to what's meaningful and important. So again, it can also help show us where are the optimal locations for those measurements, and maybe indicate how often the measurement should be made in order for us to be able to pick up the rate of change for that particular failure mode. So failure modes, we need to think more broadly about this somewhat too, in that, sorry, I just want to reset my clock here so I don't run. We tend to sometimes focus as geotechnical engineers, we may focus, say, just on stability of the downstream slope. And so we'll put in deformation monitoring systems, maybe a few piezometers, and that's it. But we really we need to think much more broadly. There are many components to a dam. The Oroville Dam, for example, I showed earlier, is an embankment dam. It's a major embankment dam. The embankment never had a problem when it failed. It was the spillway, the main spillway and the auxiliary spillway that gave problems. We've had other cases where gates failed and created real issues. So we have to think, and if we're instrumentation monitoring people, we got to think much more broadly to the whole spectrum of parts of the dam that might contribute to my broader definition of failure. And then we got to think about a much broader set of potential failure mechanisms, or what we might call triggers. And I've listed these again, I won't go through them, but these are all documented mechanisms that have occurred that cause dam failures. And so it's a good starting point just to say, I've got a dam, I'm going to be developing an instrumentation monitoring program. Have I covered which of these apply to my dam, and have I considered all of these adequately? So that's a starting point of what we might instrument. How we might do it, there are lots of instruments available to us today. There's too many instruments sometimes, all kinds of different gadgets, and it's easy to get lost in all of that. But I think it's worth just recognizing that we have about anything we want to measure, there's a sensor to do it. Again, I won't go through all of these or cover them, but If you're interested, I'll share this presentation with Professor Roja, and he can distribute it. But you can see we can measure lots of things. And there's some newer technologies too that are becoming available to us that are very exciting as to what they can do for a more global monitoring. These are all more or less point sensors. These get into more global monitoring capabilities. For example, LiDAR allows us to fix an instrument off on the away from the dam somewhere and then scan the entire outer downstream face every half hour if we want to. That's really pretty interesting, and it can detect movements down to a few millimeters, XYZ movements. LiDAR aerial, where you're doing it from a drone or an airplane to produce a point cloud and then do that repetitively, look at the difference, and from the differences to calculate vertical and horizontal movements. Again, a very interesting technology, the cost of which has come way down. Radar is being used somewhat like LiDAR, which is light, but radar being a different frequency, scanning the surface to detect movement. This was actually used on Brumadinho, or being used on Brumadinho. It's being used a lot in mining in Australia. Still working its way into the dam world. It's still quite expensive. INSAR, another very interesting technology using satellites to detect movement, moisture, and other surface conditions. Again, to a few millimeters of accuracy in XYZ directions. Sorry, I should just say Y and Z. That very complicated data processing, but it's getting better. And this is becoming more of a service available to us just to buy the images, the maps, and the point clouds. Very interesting digital camera with very high resolution digital cameras with bit mapping software that allows us to detect movement from changes in sequential images of particular locations. And so we might have something that's like a sign or that stands out a little bit. Just take digital images every hour and have the software tell us, has that image moved? And this stuff is getting to the millimeter scale now as well. Infrared cameras doing the same kind of thing, but in this case, looking for thermal changes, like what might happen if I get water starting to break out on the downstream surface of the dam or flowing over the top of the dam. The water being of a lower temperature shows up very clearly on the images and might be a very good warning indicator to us of a piping failure that's breaking out or an overtopping. GPS, these are using giving us very precise measurements of XYZ position of fixed receivers from satellites. These are highly reliable, somewhat expensive, but they're getting a little less costly, and certainly a suitable replacement for the traditional sediment plates put across the crest of a dam. A few GPS receivers can be very valuable, work day and night, nonstop, weekends as well. Automated total stations, again, another way to look at fixed targets and survey their changes in position to millimeter accuracy. These were very popular the last 10 or 15 years in special applications. They tend to be somewhat expensive, and I think they're probably going to get replaced with others like digital camera before long. Distributed fiber optic is another very interesting technology. Take a fiber cable. You okay? We take a fiber and a special interrogator, and it uses just changes in the length of the fiber to tell us strain, temperature, and vibration at close spacings along that fiber. That fiber can be kilometers long. The spacing can be down to a few centimeters. It's amazing capability of what can come back out of fiber optic. And I've seen schemes where it would say we would take the top and downstream face of the dam, and we'd run a single fiber back and forth from the top down to the bottom of the dam, and then scan that, say, once an hour, and it would give us an indication of localized movements. Conceptually, that works. As a practical matter, there's still a fair amount of work to do there to what do I do with all that data, and how do I turn it into something that's I can interpret, rely on, and make decisions. So each of these can be measured with electronic instruments. Therefore, we can automate with these instruments. A couple of examples of what an automated system looks like. and I just use these as some indication. These a modern system with radios and solar power reading an in-place inclinometer in this case. And then one I really want to focus on a bit is the grouted in-place piezometer, which is where we put multiple piezometers down the same boring and grout them in place. And people say this won't work. Grouting will keep the water from flowing, but we don't need water to flow. We need pressure to transmit. So as long as it's saturated, these work very well. And I want to give you an example of the huge value and benefit of this. This is one of those coal ash dams that is quite high in this case, about 20 meters high. And it had a potential failure surface here shown in red. The engineer assumed a phreatic surface, as many of us might. That is this dashed blue line at the top, because he saw some water standing here and he knew the water was up here and he knew tailwater was down about here. So that makes good sense for a phreatic surface. And then he assumed hydrostatic pressure conditions beneath that phreatic surface. Now this gets a little bit geotechnical, but if you bear with me, the reality is when we put in piezometers, a piezometer located here measured that height of water. A piezometer put in here with a tip here measured that height of water. The hydrostatic assumption says that that water went all the way up to this height. So I hope you can see that the actual measured pore pressures were a third to a half of what was being used based on an assumption of this phreatic surface. That simple change, that set of measurements done with multiple piezometers down, grouted into a single borehole, one borehole, two boreholes, three boreholes, that simple change in how we do things and interpret them led to factors of safety going from 1.2 to 1.5. So the dam went from essentially an unsafe condition to a safe condition simply on the basis of better information on pore pressure. This saved this client tens of millions of dollars in avoided remediation repair costs or remediation costs, because there were several facilities that were like this. So these technologies the other beautiful thing is many of these technologies can apply anywhere. This is a dam in Brazil. My Portuguese isn't good, so I won't try to say this, but Professor Roja and some of his students and I doing some work on this dam. Here's Professor Roja out doing the old classical take a picture thing, but his student uses new technology. This is a drone that allows us, we walked along the top of it, the drone flies within a half hour, all the contact areas with the abutments, lets us see all the downstream face of this dam and record it for future purposes. Really major step forward. And I suspect that every dam owner and their safety program will be flying drones in the very near future. Other types of instruments, electronic liquid levels, so we can track what the reservoir is doing. And notice that one of the things I want to show here is the extra effort that's being done to protect these instruments. Many times people take a shortcut on this, don't put those in, then the instrument gets damaged and doesn't work very well. We also now include weather stations a lot of times on sites because we're getting local weather that's different than what a station 10 miles away might say. So these are fairly cheap, inexpensive, and add a lot to our ability to interpret data. This again is solar powered going into a remote telemetry station. Data acquisition systems, which gather all this stuff on a widely dispersed site, aggregate it into a modem and send it off to some central database collection system that's all now done usually increasingly on the cloud, and giving us very nice reports telling us in real time what are our instruments telling us. We combine that with GIS mapping so that we can track what changes are happening in geometry with time. It can be very useful in surface dams, so we can keep track of the history of construction along with what do the measurements tell us. And then feeding that all into, in some cases, an automated monitoring system. This is an example of one we stood up for TVA. See 10 large screens here. Each screen can show a site, or one site can be blown up on all those screens. And the idea is if it's a real emergency, we can draw people into this room and make critical decisions quickly based on the latest data. Technology can do wonderful things for us. We just got to be willing and daring to put it to work and put the right people in the room to make sure it does work for us. Another new application I had not thought too much about, but we've been asked recently to get involved in is upgrade emergency warning systems using some of these later technologies. The whole idea is that we might not be able to detect failure early enough, but if we can get just some cases, just an hour of warning that something terrible is happening, we can get people out of the way. And so I think these technologies really need to be thought more about how they fit into a good emergency warning system to help save lives. As a part of all this, you've got to be prepared to act quickly. So we talk about performance states as normal, caution, alert. Normal being green, caution being yellow, alert being red. And in here, I've defined these a little bit more carefully. I've gone into some details here as to what might be used to establish a threshold level and a limit level, and what actions you might take. At limit levels, you stop work and you undertake some protective measures. You enter into some contingency planning, but you don't do the planning then. You've already got the plan thought out ahead of time and you implement the plan. And that's a really important part. I see in many cases, people don't develop that ahead of time. Then when the red warning comes, they don't really know what to do. A bunch of meetings occur and you can't get agreement. That's too late. You need a written contingency plan that's clear, unambiguous, and lays out when you have to do what. So data and information are coming with these systems. A lot of it, we can get overwhelmed quickly. Geocomp collects data on like 50,000 sensors a day, some of them as often as 100 times a second, believe it or not, in some of our bridges. That data and information has got to be processed. Data quantifies performance, but it by itself is not enough. We need information, context information, to give us what's called situational awareness. So that might be things like documents, cameras, video, visual reports. All that needs to be combined together so that the data and information is up to date, on time. It must be accurately describing the performance state. It's got to get to decision makers in a form that they understand. And then they got to be prepared to take prompt action when it's required. Some of the examples I showed you, there was very little warning that a major failure occurred with big consequences. These are just some stuff that I've put together over the years. I won't go through here, but what these different action states mean and what your response at each action state might be. These need to be laid out clearly for a project so that everybody understands what their role is and what they need to be doing when an instrument goes yellow or when it goes red. Let me skip over that part. I want to emphasize visual monitoring remains very important to all of this. We can't put an instrument everywhere. And so what's missing, we do see people do visual inspections. What's missing is an action plan. So if you see certain things, what does that mean you must do? So you need to try to work through those, and this will give you an example of how you might do that. Let me skip that one. So why monitor in real time? It's because failure can occur rapidly with very little visible warning. Even for a dam that has functioned well for many years. The examples I gave you had very little at the beginning, had very little visual warning, and yet the consequences were quite significant. Failure may be avoided using preventable pre-planned actions if we have an adequate warning. At the very least, we can get people out of the way, which can considerably reduce the consequences. So if we've got real-time monitoring, we're better able to connect cause and effect as well. We can understand better why are things not behaving the way we expected. And I quote from a paper by some of our leading colleagues here in the US who work for the Federal Energy Regulatory Commission, our main dam safety regulatory. Results of a dam safety surveillance and monitoring program should be evaluated on as near a real-time basis as practical. And I would say as practical today with automated systems is within seconds to get the data to you and then a few minutes to evaluate it and make a decision. That's what the state of practice can bring us. So keep that in mind, please. So there are a lot of benefits for doing this quickly. And I've already mentioned a couple of these. I'll leave that. I just want to make a couple of key points. Data by itself is not enough. We need the contextual information. We got to do something called evaluate and interpret, and that gets us to actionable knowledge for making informed decision-making, for doing informed decision-making from which we take action. This evaluation and interpretation is really important. You need to separate them. Different people do these. People mix this up. Evaluate means, do the data make sense? Can I get rid of all the nonsense? Can I pass along an evaluated set of data that are clean, that are believable, so that when it gets turned over to the engineers for interpretation, they don't have to ask questions like, can I believe this data? They ask questions like, what do I need to be doing? So we want to have a system that helps separate these out and do these actions very reliably. These can take a lot of time of well-trained people, but if you don't make that investment, you're not going to succeed. Systems help us do this. New modern web-based monitoring systems help us bring all this data and information from different sources automatically into a central management system where it's available 24/7. Deliver it out to your phone, your laptop, your desktop, any of your devices working across different platforms. So your phones could be Apple, your laptops could be Microsoft Windows, etc. And getting it out to all the project party members. We can control what information goes to who, but you can make selected parts of this information available to selected people. And you can do that in forms they can digest quickly, either as typical reports put out as PDFs, or I missed a slide here. I thought I had something. Or as on your phone, report on your phone. So this is the future. The web-based monitoring is where it's at. The presence of these data warehouses are very cheap now and very secure. We'll see that coming more and more, and it's going to help us do our job much better. I've listed key elements of an effective performance monitoring program. There are a lot of them here. Pay attention to these. We don't have time to go through all these, but you really need to kind of work through each of these and at least make a conscious decision of, yeah, I've got that covered, or no, I don't. Key parts I want to point out is most instrumentation monitoring programs to be successful need a champion. You need somebody to understand, why are we doing this? What's the value and benefit? So they can go argue to get the money to do it and to maintain it and keep it going. Without that, it will die. And you can't always do these things on the cheap and have them be effective. So there are 5 steps. I don't really have that much time to go through these in detail, but I think you'll find them useful. What to measure and where, how to measure it, develop and apply methods to make it all work. And we hear a lot that people say, well, I don't want to do instrumentation monitoring because it never works. That's just not true. You know, it doesn't work if you don't get the right people and the right team on board. But if you get it, it can be, you know, almost entirely successful. We have projects over and over where we end up well in the 90% plus of all of our instruments functioning a year later. But you've got to follow good technique, good practices to make that happen. You collect the data, define what to do with it, and then take action. And that taking action, you got to know what to do, you got to be prepared to do it, and do it quickly. So carry out and document these steps systematically are also really important. One other key question, who should be doing this kind of work? I think it's the work of specialists. Unfortunately, we see a lot of this work put out as a low bid contract, which means it goes to the lowest cost vendor, who's going to take shortcuts and wind up with a system that you have to live with for your life that is the result of a low bid contract. So they usually don't deliver best value in a long-term sense. I urge people to try to move towards qualifications-based selection. I've seen so many instrumentation programs involving millions of dollars that unfortunately never delivered the value they could have had they been done by qualified people. So just a summary of some key points. Use potential failure modes analysis to help you lay out the actual locations, types, and numbers of instruments. Use a systematic approach, which I didn't get into in this, but I've written about it. So there's and Professor Dunnicliffe wrote about it too, step-by-step process. Operate in near real time with your data and use automated messaging to communicate results across people. We do this all the time now with emails, sending graphs and messages and alert messages. It makes us much more responsive. We need data and context information in a form that's readily understandable and interpretable by not only technical people, but by managers. We produce reports sometimes at 8 o'clock in the morning to a project manager, which the message says in text, everything's okay. That's a great value delivered to that project manager. He doesn't have to worry about his instruments, his data, and his performance. He can worry about money. This system should be designed to operate throughout the working life of the dam. This is a shortcoming of many instrumentation systems. And we need to have clear lines of responsibility and communication, top to bottom with training and coordination. I didn't talk about that much, but many times we find things get detected in the field, malfunctions, poor performance. It doesn't get communicated to a key decision maker. Need to have a champion, and the fund needs to be adequately funded and staffed to be effective. And it's got to be executed by qualified, dedicated people. Not dedicated is really important too. Instrumentation is special. You got to have some people who are willing to work at night and on the weekends when things demand that it does that. And so that sometimes those people are hard to find. So I'll stop at that point. I think that's a good ending point. And I apologize for talking so fast in a second language for you, but again, I'll share my slides.
Well, thank you very much, Dr. Marr. Oh, sorry. Well, thank you very much for your very interesting presentation. And you, in a very short time, present a very good and excellent sequential of slides that can really show the attention what we really need for a good instrumentation or monitoring program. And it would be very helpful if you could share with us this presentation. I'm sure many of us will have the benefit to have it, you know, and to, in some way, I could say, to digest all the information you have on that. I think now perhaps I would like to have the help of Alessandro Cironi, because we have the YouTube as well. People are watching YouTube to make some question and some point to discussion. And I'm not sure that I'll be able to follow the YouTube, but Alessandro could help me, if please.
Pedrito, feel free to ask your question first to our speaker.
Ah, that's no, sorry, I don't have a question now. Of course,
no, okay. So we have science. We have science.
It's not a question, but perhaps a point to discussion. But you mentioned about you know, these high readings, and they can sometimes be misunderstood. You know, is that a warning or something like a false reading? And I believe so. By saying that, I think we come to the redundancy. We must have some redundancy. Just is not be based in one reading or one instrument. So could you say something about that? That would be the first question. And second, I think that when we come to all this modern technology at our disposal, it's time perhaps for us to say something, and I would appreciate if you say something about machine learning. Okay, maybe these two questions, well, not questions, maybe some points for discussion. And after that, I'll leave it to Sion to say something.
Yeah, very good. I mean, those are very good questions. And, you know, let me take the high reading and actually divide that into two issues. You said high reading, you had redundancy. In some ways, those are two different things, because I can have a high reading and it's real for that instrument, but is it indicative of the overall situation? So that's where, if I like to say, when we design a system, if I've got a critical instrument somewhere, I don't want to be dependent solely on what it's telling me. because it might be wrong. It might have changed readings over time, might have been damaged. So if it's a really important instrument, I need some redundancy. That is an independent way of verifying that that measurement's good. So it might be a sister instrument located nearby, or an instrument, one's measuring pore pressure and one's measuring deformation. So I can say I got verification that something is happening here. So that's one piece of it. The other piece, a high reading. A high reading can happen just because of errors in the electronic system somewhere or other, a data glitch of some type or other, or somebody bumped the instrument, or I had a lightning strike, or just things that we can't really, we never really fully understand. Some rogue minor particle went through the computer system and screwed it up. So you adopt some methodologies for doing that, such as, if I get a high reading, go back and read it again. And you can do that with electronic systems. Give me another reading. Let me see if I can repeat that high reading. And if I can repeat it, then I'm much more possible that it's real. We can use some data processing techniques to try to clean, what's called cleaning the data. You basically compare that reading with things in the past or behavior in the past. And if it's something that's happened before, then probably it's not a fair indicator. But if it's brand new and novel, and you verified that it's a true reading or it's an accurate reading, then you got to think about it. So go back and check it, make sure you can validate it, verify it. And that's where the role of machine learning can come in. Machines can do a really good job of some of these checks as long as we can formulate the logic that the machine wants to use. And that's what concerns me in some of the research work I see going on right now. Just blindly applying machine learning to a big set of data can find patterns that really have no physics underpinning. And so machine learning has to be used with some real care, or it can mislead us. And some of the key people that are behind machine learning will warn us, will tell us that artificial intelligence and machine learning is no substitute for expert review and expert thinking. So we got to combine those two. Machine learning, artificial learning should be a tool for people like you, Patrico, to amplify what you're able to digest and deal with. In the end, key decisions, though, have to weigh with human beings, I think.
Thank you. Over to Sayal. It's your time now.
Okay, sorry, it was mute again. First, let me thank Alan for this very comprehensive lecture on instrumentation. Very good and very important for all of us here in Brazil. Alan, I have 2 or 3 quick questions, and I apologize for bringing the discussion to the point that we are most interested now, that are our tailings dams. Of course, our tailings dams, recent accidents are still in our minds, and that's why I will ask this question. First, I will start with the most recent one, Brumadinho. You mentioned about it. You also spoke about a radar monitoring system. Do you think, in your opinion, if we had that in Brumadinho, that was a very fast accident, would we have time to avoid the accidents with these real-time systems?
So I've studied the report on Brumadinho by the independent group, and a couple other reports are out. I think they're pretty unanimous in that there was very little warning out of that instrumentation system on Brumadinho, which consisted of some piezometers that had been recently connected into an automated monitoring system, but that wasn't totally complete. It consisted of the radar system, which was scanning, I think, every few minutes. That radar system, as I understand it in these reports, says that there was no indication of any movements other than noise in the monitoring system. So I think that's to me, that's a real wake-up call to us who work on instrumentation systems for tailings dams, that there are certain failure modes of which Brumadinho experienced, which are brittle failures. That means there's almost no warning in the way of movements in advance of it actually collapsing. So that tells us, wait a minute, deformation monitoring systems for that type of failure mechanism may not help us very much. So what do? We have to go back to make sure we better understand what the water conditions are in that dam, what the pore pressure distributions are, so that when we make an assessment of factor of safety, it's reliable and it's telling us a real factor of safety that's well above that's above acceptable limits. We just have to tailor the monitoring system to something that we can work with. And in that case, the evidence is that anything that was trying to monitor deformations would not have given us much warning.
I agree completely with that. Yeah. Very, very fast. Even the real-time radar monitoring system would not be able to prevent, to give the signal to evacuate the area with time. It was very, very fast. But okay, the other one that you mentioned that deserves some discussion, the case of Mount Pony in Canada, that accident, you mentioned that could be perhaps due to shear-induced pore pressures, because the foundation material was over-consolidated and became normally consolidated, generating positive pore pressures. The question is, how can we put instruments in the foundation to be sure we are going to measure those shear-induced pore pressures? Very difficult, because you don't know where the shear will be happening.
Yeah, very good question. And we have to be careful looking backseat driving, quarterbacking. I don't mean to in any way say engineers should have done this or should have done that. That's what can we learn, and what we can learn from here. One of the problems, of course, is that some of these failures, like Kingston failure, there was an unknown layer there of weak material, and that if you don't know about something, it's really hard to figure out how you can instrument exactly that layer. But in the case of Mount Poly, I can't prove this, but I really suspect, based on soil mechanics principles, that there were shear strains developing in that soft clay layer that would have been revealed by an ankleometer that passed through that soft layer. We would have seen those shear strains start to develop in a fairly concentrated zone, and to an alert, knowledgeable engineer, it would have been a warning sign. I suspect. I can't prove that, but just with my knowledge of geotechnical engineering, I think that would have been very helpful to us.
I agree.
Pore pressures, they did acknowledge they had piezometers that were in that layer, but they were there were more hydraulic type piezometers, which have a lag time to them. Had they used the more modern electronic transducers grouted into place, they respond almost immediately. And that technique would have indicated shear-induced excess pore pressures.
Yeah, okay, but this brings us to another point. Most of our dams in Brazil are, and perhaps in US as well, are instrumented with hydraulic piezometers and not automatic piezometers. So can we understand that you recommend reviewing all these and perhaps changing the instrumentation system? Is not very expensive.
Well, I think yes, we ought to be on a review. I mean, some of these you know, the instrumentation in Oroville Dam was put in 1960 something, and it hasn't been updated since then. God, you know, suppose I was still driving my airplane from 1960 across the country. I wouldn't be too comfortable, right? At some point, these structures, we have to look at them, and the ones that pose substantial risk to our livelihoods and our populations really need some serious consideration of, you know, don't we do a better job on some of this? And I know money's short, but we find it when something breaks. They found $1.1 billion to fix Oroville Dam spillway after it broke without much debate. You know, can't we find some money to be more proactive up front and prevent some of these things?
That's true. Before we change subjects, my last question about these tailings dams. Are you familiar with current regulations in Canada and US on tailings dams? Are those upstream dams still allowed? Because in Brazil, they are not allowed anymore.
Yeah, I'm pretty familiar with that for various reasons. I'm actually on a steering committee for the USS dams right now, trying to write the next generation of design. I forget what we call it, design manual, design guidelines, something like that. And a couple other committees. I'm pretty familiar with it. And it's evolving. You know, I know Brazil, after Brumadinho ruled out upstream tailings dams, I think I'm on record publicly of saying, I don't think that's necessary, that I can design, or you could design an upstream tailings dam that if properly built according to that design, it would be just as safe as or it would be safer than for a poorly built other method of construction, right? It's all about, it really is all about methods of construction. And you know, we can design, we know how to design these things very well if we've got the right people on the design team and the right reviews. But the problem in tailings dams is that we don't, as designers, have much say or control over what actually gets done in the middle of the night, when things might depart from best practices for a few hours or a day or 2 or 3 and leave a weak seam in there that goes undetected and then shows up 20 years later when it fails.
Yeah. Okay, I don't want to dominate the discussion. Maybe Alessandro and Pedrito have some other questions from the audience for you. If not, we can go on.
Alessandro, if you can help me with YouTube,
Yes.
maybe you have some questions from people there. Yeah.
Yes, we have.
Please carry on.
The question from Corrado Piazentin. He's asking, most dam failures and emergency situation were detected by visual inspection, not by instrumentation. Is it true? And he continues, in my opinion, thorough inspections in many situations are more effective in detecting problems or to indicate where instrumentation should be installed. Do you understand the question?
Yeah, I do. Yeah, good question.
Let me just explain. Corrado is a very well experienced dam consultant engineer here in Brazil.
Yeah, he's got an excellent question. Very indicates a great deal of practical knowledge in this field, and he's right. But you know, we have to be careful. It takes both. And I tried to say this in the lecture. It really takes both. There are things that go wrong below the surface of a dam that are early warning signs that you really can't detect with visual inspection. So instruments really play a good role there. But the instruments are mostly point source sensors, right? And so you may have something going wrong that's visually obvious and doesn't show up on your instrumentation. So having that visual inspection is very important. But there are these stories too, such as Brumadinho, which was visually inspected a few days before it failed, and nothing was picked up. So, and I don't think it had been inspected any number of times by different people in the months leading up to the failure. I'm not saying those visual inspections were deficient. I'm saying there was no obvious visual evidence that dam was in a troubled state. So it takes both, in my view. And I just would add, and I try to make this point, I'm really encouraged by how much more effective we're going to be in visual inspections using drones. You know, I used to spend a whole day climbing around on a dam. I'm getting too old for that now, and I won't be as effective doing it. But give me a drone, man, and a good drone manager, and we can do a lot in a half a day.
Peter, do you want to add something?
No, I could add that both in Brumadinho and the first one that was Fundão dam, both of them had problems with the drainage systems, and these were known. So they gave some previous sign.
As a coordinator, I'm going to use
Sure.
my hammer. Perhaps Alessandro has more question from the audience, and perhaps we leave me and you for the end. Again, Alessandro, carry on, please.
I received the question on WhatsApp, but it is in Portuguese, and I ask Pedrito for help to help
Can you
me translate. Okay.
Can you say to me?
O pessoal aqui da minha empresa, eles perguntaram o seguinte: é comum fazer a carta de risco com base em leituras piezométricas, porque é possível associar ao nível freático um fator de segurança. Como é possível fazer isso monitorando deformações? Quais são as sugestões do Alan a respeito?
Well, Alan, the question is that it's quite common to make this chart, the risk chart, based on piezometer readings. And so this is something that's quite a normal practice in Brazil or everywhere. But how can make this risk chart based on deformation, displacement from inclinometers? Do you have any suggestion?
This is tough. You know, how do you decide, you know, how much horizontal displacement from an inclinometer is going to be your yellow alert and how much is going to be your red alert? And that's always a tough question, because it really forces an engineer to kind of put it on the line, his prediction of what the behavior is going to be. And that's a challenge. The way I look at it sometimes is that I use all the tools available to me to try to estimate what value or what reading would cause me to start to lose sleep at night. You know, it's got me concerned. It's got me nervous. There's something a little different. This is not exactly what I expected. That's the point where I ought to be getting into the caution zone. And, you know, I can get that by rule of thumb, by experience, by advanced finite element analysis, whatever tools are available to me. But at what point I'm relying on this person that's doing this to be experienced and knowledgeable. And then the next level is really, what is it that I can't sleep at all at night? I'm really worried, and it's aggravating me. I just can't be sure I can guarantee this. Or what does my advanced numerical model tell me is way out of the range of anything that's within reason of a parametric study in my numerical model. At the end, you're setting these numbers is engineering judgment, and engineering judgment's a little flawed sometimes. So but we have to do something. And we really need to try to do this when we're clear thinking out of the crisis of the moment, and using rational reasoned judgment and whatever tools we have. But think of it as caution, yellow, when I start to get nervous and concerned and things aren't, I don't understand everything, and red, can't sleep at night, I'm really nervous and things might be at risk.
Alan, can I add something on that? Perhaps would it help that instead using the displacement itself, this measurement, we could use the rate of displacement.
Yeah.
Rate of displacement, maybe we could differentiate the creep in the first stage, second stage, and third stage. And that could give us some idea about this movement. Do you agree?
Yeah, I totally agree. I mean, it doesn't change the difficulty of predicting what is an acceptable rate, what is a warning rate, what is an alarm rate, but it is another way of looking at it, and it is very, very worthwhile. And in fact, in some of our monitoring systems today, we look at not only what is the reading relative to limit values, but what is the rate of change. You got to be a little careful, though. In the computer system, when you compute rate of change, you can have over a short time a very high rate of change just because you got a few inches of rain last night, and so that can throw you off.
Okay, Alessandro.
We have no more questions in the chat.
Okay.
I think I talked too fast.
I did quite well.
No, the audience is shy. Don't worry.
Well, let me perhaps ask your opinion about still the same subject, failures and perhaps warning systems. Do you recommend assessing safety with probabilistic methods, as everybody is trying to push harder into new practice? What is your opinion about that?
Well, I have, I guess, mixed feelings about it. Probabilities are really good to guide us, I think, on public policy issues and are we safe enough? How safe should we be? I think that's really helpful. I think it maybe is a helpful tool to those who understand probability to help make design decisions. But then we wind up, if I'm the designer of the dam and I'm putting my stamp on those drawings, do I really want to think about a probability of failure? Or do I want to do my best job using standard of care and design guidelines to design a dam that should be safe? So you kind of have a philosophical divide or problem that goes on there. I will put my stamp on something that by conventional practice says the factor of safety is greater than 1.5. But if you had next to that the probability of failure is 0.0005, I'd be kind of nervous about adding that statement onto that set of design drawings. I don't think we've really evolved as a society yet to understand and use that information.
Yes, you are right. The problem is, where is the yellow number for that probability? You mentioned something about 10 to minus 4, but I don't know. We need more experience, more analysis to be sure that 10 to minus 4 would be a number to be recommended or not.
Yeah, when I was working on the repair upgrades of the levees in New Orleans, and I was explaining to some of my neighbors and my children that the Corps of Engineers was authorized to rebuild them to withstand a 1 in 100 year flood, they said, "What? You're going to really design something that could fail in my lifetime?" They didn't understand it. They couldn't buy it. And I said, well, I'm not happy with it either, but you need to talk to your congressman and convince them to put the money into taking this to more like 1 in 1,000 or 1 in 10,000. That we've got a long conversation that has to happen to get to the point where we get clear guidance and funding, and all of us as engineers would love to do that stuff, right?
Yeah.
We'd love to get it up to 1 in 10,000. We'd love to have all these facilities much safer. But in the end, somebody's got to pay for that.
Yes. In other words, total safety means infinite dollars.
Yes.
Yes, that's true. Okay. It was a very comprehensive lecture, as I said. I thank you very much again for
Well, I still have another question.
Okay. Okay, go ahead.
You're finishing.
No, I was passing on to Alessandro to see if there was any order, but maybe you go ahead, Pedrito. You are the boss here.
Alan, you see, normally, you can see clear that normally when we talk about instrumentation, people normally concentrate in piezometers to measure power pressure and displacement. You know, you have this sort of in place inclinometers, and now with this remote sensing, you can have some superficial measurement as well. But we can see that one very important aspect of safety of them is related with the total stress. Your PhD thesis was in total stress, and we know that's quite hard to interpret. There are many sources of errors involved with the total stress cells. But you know, when we talk about stratigraphy, internal consolidation, and the load transfer mechanism is very important for the failure. You see, sometimes you can have very low pore pressure, but if you have a very low total stress, the effective stress is low, and you can have some liquefaction and then failure. Would you say something about that?
Well, you're absolutely right. You know, and you know, this whole thing. You know, for example, a hydraulic fracturing mechanism. You know, we don't still really know the stress conditions that lead to that, or we may have stress conditions that are different than we expected that could lead to hydraulic fracturing. You know, as you're right, I spent years on that topic, and I got to the point where today I rarely put in pressure cells because they, you know, I say when I teach this, if it gives me the answer I expected, it's good. If it gives me the answer that I don't believe, it's no good. So why put it in? So, and that's unfortunate, but you know, maybe we'll get some technology improvements. You know, it would be great. It would be a great step forward for us. But as we stand right now, we can probably do as good a job calculating it as we can measuring it.
It's very interesting. It's very interesting that we still have, when we're measuring stress, we still have something to calibrate. That the vertical stress is only due to the gravity. Mm-hmm. You know, that's something that you have to put in our mind. The horizontal stress, either in one or the other axis, is different. But the total stress, if we're measuring it and we cannot calibrate it with the vertical gravity stress, you know, it means that either our instrument's not doing well, performing well, or we have some load transfer that's, you know, piping, or even not only piping, but even, let's say, we could have some development, some triggering effect, you know, failure process by back progressive failure in some way. So
yeah, it would have been very insightful if we somehow magically had a bunch of stress cells within Brumadinho that could tell us how that that failure was evolving, or you know, what happened in the days before. I'm not speculating. I'm just, you know, that would be very insightful data.
Mind you, in Feijão Dam, in Fundão Dam, that was the report by Professor Morgenstern. He said it was something like a load transfer during consolidation, you know, and so because you have some consolidation and you have some weak deposits like this line, so that could be caused this development of a failure surface. But always in this case, always relate with the load transfer mechanism, internal load transfer mechanism.
Yeah, that's a very credible triggering mechanism, I think, and potential triggering mechanism for liquefaction in some of these dams that are zoned or that have different properties. I think there's some subtle stuff that goes on there that we don't understand fully. We may not understand, and having those measurements would be insightful, but I don't know how to do them today with any reliability.
maybe I would like to put another. Is there any question, Alessandro?
Yes.
Okay, you go.
Two last questions just showed up. Dionis Barbosa is asking, Alan, what are the application of visual inspections using drones in tending dams? Could you tell us some of your experience?
Well, I think I tried to say my delight and my enthusiasm for using drones for doing these inspections. I think I can foresee the possibility that we have a drone permanently employed on a dam to go do a visual inspection to ensure us that we don't have a rapidly evolving situation, such as a internal piping or internal erosion or an overtopping. I mean, I'm trying to design an emergency warning system right now for using newer technologies for a particular location. And drones are a key part of that, I think. One, in helping us lay it out, and two, and eventually being able to deploy them to, if we have signs of a condition, that visual information is so valuable, so much more convincing to me than a single reading off an instrument someplace.
Okay, we still have a question from Corrado Piazentin, but now is asking your experience with failure of gates. He says that one special aspect is the failure of gates in dams, especially the bottom gates. What is your experience with this aspect? Because it's also continues here. The dam owners are reluctant to operate these gates to check if they work properly.
Yeah. Well, I'm a geotechnical guy with some peripheral experience on other aspects. I was on a World Bank team looking at some dams in Afghanistan, and gates were the big problem. These dams were built by the Soviets in the early 60s, and you know, they were exactly that. They were very reluctant to operate them, and yet, you know, the standard practice is you got to operate them periodically, at least once, if not more times a year, to make sure they're going to work. I just think that's essential, and I don't know how else to say it. They've got to. They're a key part of the safety of the dam, and somehow they have got to get the attention to make sure they're going to work when they need to work, and they need to have redundancy in their main operating systems. Again, that's not my expertise, but I'm just an engineer where that seems to me to be so logical.
Okay, I think that we can proceed to the end of this seminar. Pedrito, would you like to spend some words for
perhaps
closure?
It's something out of your presentation, Alan, but you mentioned about John Danicliff's book. That's one reference of instrumentation, and as you said, it's quite unique, you know. But perhaps it's time for us to think about the book. You are one of the authors. This book, by the way, you cannot buy it. Alan gave me as a present, and this book is the title is Dam Safety Performance Monitoring and the Data Management Best Practice. And this book was financed by the Center for Energy Advancement through Technological Innovation. It's a fantastic book, really. And I think being one of the authors, Alan, you should try to make it in a test book, you know.
Well, I thought about it, you know, when I retire, maybe I'll take this up. You know, I was doing this lecture today and I was thinking, you know, this is kind of the thread of, you know, a full theme, you know, that would be nice to expand out at some point. But, you know, my life is pretty full of lots of to-do things and promises, you know, so I don't know if we'll get to that or not. But, you know, John's book's excellent, but it's out of date in many ways. It has nothing on modern electronics and modern data acquisition systems and some of this management practices that are so important now. And John would agree with that. He and I talked at one point about jointly updating the book, and we were both just so busy that it just wasn't going to fit in. And unfortunately, he's now gone. But maybe I think there's there's a need. And I also think now too that we need to think of instrumentation, and some of you in the audience might benefit from this, more broadly than just dam instrumentation or geotechnical instrumentation. Those of us who work in this field have valuable contributions to make in all types of instrumentation of civil works. So, you know, my crews that do geotechnical instrumentation on dams can do just as well on bridges or on buildings. And the key there is that we get good, well-trained instrumentation engineers who do some of the things that I talked about today well, and they will serve our whole civil engineering profession.
Oh, good. Also, be looking forward to have your book.
Well, maybe I should retire and come down to Brazil and live with you for 6 months while we eat and drink wine at night and write in the daytime.
Oh, that's good. Yes, I agree. And also is worth mentioning about another icon of instrumentation that's recently passed away. That is Elmo Di Biagio.
Oh yeah, thank you.
That's good working on instrumentation from NGI. Well,
yeah, the grouted in place piezometer that I mentioned is not new. It's new and being used, but it was actually developed by one of your colleagues, Professor Vaughn,
yes,
in 1962, and it just lied around, never got used very much. But it's a huge step forward that we should be making use of, a lot more use of in dams.
Anything, Alessandro?
No, I think that we can spend some word for closure,
Okay.
if you want, Pedro.
Okay, Alan, thank you very much. You know, always nice to hear you talking about instrumentation and engineering practice. And I'm sure all the audience enjoyed very much your presentation. Fantastic stuff and a lot of experience. Thank you very much. And as you said, I hope this pandemic will finish so we could have together having a caipirinha and enjoy some Brazilian food. Thank you very much. My best regard to Dixie. Okay.
Yeah, thank you all, and say hello to Sarah, please.
Thank you.
Goodbye.